Now, okay, some of the basic concepts here. So the first thing is that we say the CAN is a multi-master bus. So it's not like that there's one device, one controller that's in charge of the bus is sending things out to different nodes. Many different devices that are connected to a CAN bus can become the master at a given time. And we'll see how that is worked out with arbitration so that we don't have a conflict if several different nodes try to become masters at the same time. And another one of the basics of the CAN protocol is that each of the different nodes, they do not have a specific numerical address. So if one node tries to send something to something else, it doesn't say target node 42 or 49, for example. And the way that situation is worked out, the way that it's decided in terms of who should take the information that's on the bus, this turns out it's actually inherent in the data stream that's sent out. We'll look at the format of that, but there's something called an identifier within the format of the data frame, and it's by using those identifiers that each of the potential receiving nodes can determine whether they are the node that should accept that particular message. And so the way that the CAN communicates, sometimes it's called broadcasting in the sense that whenever a message sends out, all the other nodes see it, and multicasting in the sense that there can be, more than one source of, not just one master sending things out. There can be several devices that can send out messages to the others. Okay, so let's look at the diagram at the top of this page. And this shows that, for example, the signal, the bus itself is down here at the bottom. Usually this is implemented in terms of a twisted pair of wires terminated at each end with a 120 ohm resistor. And then between the microcontroller and that bus, usually there needs to be something that's called a transceiver. This is something that makes sure that the signal levels are compatible with the signals needed on the bus. Some microcontrollers, such as the ones that we're looking at in this class, actually have the CAN system as a subset within the chip. And we'll look at that particular feature as part of this unit. Some microcontrollers, though, don't have that, in which case you'd have to buy a separate chip to go along with it to make up the part that connects to the bus through the transceivers. Now, one thing as we go through the unit here, then we'll see as well, is that there are a number of error checking detection mechanisms. With implementing it in the automobile, it's a high noise environment, and so there's a high potential that there will be errors from time to time in transmitting messages. So there has to be a fairly sophisticated means of detecting and dealing with errors, and so that was built into the CAN system because of the kind of applications that they were developing it for. Now, the way the signals are actually represented is using something we called before the non-return to zero bit coding. That simply means that throughout the time slot that a data value is represented, it will either be low or high throughout that bit period. So, very similar, for example, to the serial data stream that we looked at for the SCI and the SPI that we talked about early in this chapter. They also use something here called bit stuffing, which is a way to make sure that the synchronization between the various devices is retained during transmission. Basically what that does is forces the signal level on the bus to change after a maximum of 5 bit periods, even if the normal data would not require that to happen. We'll look at a diagram to show that here in a couple of slides. The CAN bus is set up to work with a very high rate of transmission, up to 1 megabits per second, with a length of up to 40 meters. And if any reason you need to have the data line, the bus line, to go longer than that, then the transmission speed goes down. the way that it handles the possibility of several different nodes trying to send information at the same time, it uses a method that's called carrier sense multiple access collision detection with non-destructive arbitration. That means that it can actually check out within the protocol which one of the devices ultimately has the most priority, and do that without losing any data. It also could do it without losing any time, which is very important. Now, we mentioned before that the messages, the frames that are sent out, they're actually sent out in a broadcast format, which means that all the nodes in the system receive all the transmissions. And the messages do not specifically indicate who's supposed to receive them. It does not contain a node number that indicates that a particular numerical node is supposed to receive that message. Instead of that, they use something called content addressing, which means that the content of the message, some of the bits there inherently indicate which node should accept that particular message. Now, the way they do that, the way the local nodes look at that incoming data and decide whether it's meant for them, is they apply what's called filtering, local filtering. And we'll see how that's done, but by looking at the bit pattern that comes in and making the filtering or selection, that means that the interesting or the pertinent messages, the ones that they've been set up to accept, they will recognize that and save those messages. Others they'll just ignore. They're all brought in initially to be evaluated for possibly being interesting, but if they're not interesting, then they'll be overwritten by the next thing that comes in. They're not stored as a valid data input for that receiving node. Now, the messages that are sent with the CAN format are short. The maximum message length is only 8 bytes because, again, this was designed for a control type application where it's sending fairly small bits of information at any one point in time to some other nodes, say in an automobile, so they did not have to handle a large number of bits within an individual message. So maximum of 8 bytes within each frame.